This video will be going through topic 3, making use of energy, the practice booklet from class. You can use this to fill in any answers that you missed or if you missed any lessons. In lesson 1, we started by looking at the density of a regular solid. So we have an example of a cube of cheese and we're trying to work out its density step by step. So part A is to work out the mass of the cheese cube. If you read the questions, the balance read 0 before we put the cheese cube on there, and now it reads 59.4 grams, and that's all it wants for the first mark. This is a foundation question, and that's why it may seem a little bit simple at some points. Part II, write down the length of one side of the cheese cube. We can see our cheese cube is right on top of a ruler, and it's 3 centimetres per side of our cheese cube. Part III is to work out the volume. Length times width times height is a 3D shape, so we're timesing it by 3 times. For this specific equation, please use a calculator. You might think you can do 3 times 3 times 3 in your head, but more often than not, people say it's 9. It's not, it's 27. So that's our volume. And then the last one, there's lots of error carried forward marks here as well, like for the previous question, but this is density, is mass divided by volume using the answers that we've previously got. So our mass is 59.4, and we divide it by our volume, which is 27, and the answer is 2.2. So up until here, we've got 2 marks. The final mark is for our unit. We have to look at the units of our mass and our volume. It's grams and centimetres cubed, so therefore our unit is grams per centimetre cubed. Part B says a worker at the cheese factory suggests the mass of the cheese cube should be measured more than once and why is this good scientific practice. So you've got 3 options to get your 2 marks. 1 is to check the repeatability, 2 to calculate a mean, or 3 to identify any anomalous results. Part II, state how these measurements could be improved, and that's by using better resolution instruments. So for example, you could say using a more accurate measuring balance, but you'd want to specify it would measure in milligrams or more decimal places, and same with a ruler, more decimal places or millimeters on your ruler. And for part C, we've got a multiple choice question. We need to tick 2 boxes because it's for 2 marks. It says we've got a cube of cheese that we cut in half and then we get a large piece, or we could also cut it in half and in half again to get 2 smaller pieces. Tick 2 correct statements. So the first one of the small pieces of cheese is a third of the mass of the large piece. That is not true because the small pieces will be half the mass of the large piece. And same for the next one. One of the small pieces of cheese is a third of the volume of the large piece. Nope, a small piece of cheese is half the volume of the large piece. Statement 3, the 3 pieces of cheese have the same density. That is true because they're the same material, they will have the same density throughout. The next one, the mass of the large piece of cheese is half the mass of the original cube. That is correct. The large piece of cheese is half the mass because we cut it in half. And the last one says the mass to volume ratio for each of the 3 samples is different. The mass to volume ratio is a different word for saying density. And we said earlier they have the same density because they're the same material. So this one is not true. And here's the mark scheme for that question. Lesson 2, we started looking at practicals and how you might work out the density of an irregularly shaped object. So for this question, it's originally asking us the volume of the object. So we have the mass, we have the volume of water in our measuring cylinder, and then we had the volume of water once we added our item to the measuring cylinder. And we can see that it went up by 5 centimetres cubed because we had 25, it originally was 20, it's gone up by 5. So the volume of our object must be 5 centimetres cubed. Then we need to use an equation to work out the density, and we can check page 2 if we've forgotten, but it's mass divided by volume. So we've got 15 grams divided by 5 centimetres cubed. 15 divided by 5 is 3. We can double check the units, grams per centimetres cubed. Part III says Fion thought the object was made of aluminium. Use the data to explain whether we agree or not. So we calculated the density was 3, aluminium is 2.7. That is the closest in all of that table of values. So to get the marks, you have to specify that you've looked at 2.7. You want that somewhere in your answer. You want to say, yes, you agree. That's because the 2.7 value for aluminium is the closest value to 3. Part B of that question talks about an object that floats on water and how could we change the experiment. So first you want to submerge your object using a sinker or a weight. You then want to mention you're still measuring the volume of water before and after, but the difference is that you'd also need to subtract the volume from the sinker as well as subtracting the initial volume of the water to find out the volume of your unknown object. The extension is a 6-mark question going through the method of how you work out the density of a small pebble which is not a regular shape. So when you write a method, make sure you put numbers down the side just so that there's nothing they could subtract marks for. So if we quickly go through this one together, first you want to weigh the mass of your pebble using a balance, then you want to add an amount of water into a measuring cylinder. It doesn't matter what amount, but that's a sensible number, 25 centimetres cubed. Then you add your pebble to the cylinder and record the new volume. Calculate the volume of the pebble by subtracting the initial volume of water from the final volume. Step 5, calculate the density by mass divided by volume. And 6, you want to give the answer a sensible unit, for example, grams per centimetres cubed. And here's the mark scheme for those previous 2 questions. Lesson 3, we looked at heat transfer, so this first question is on conduction, and it's a 6-mark question. It shows us the practical we looked at in the lesson, where we use a Bunsen burner to heat 4 bits of metal and we see which one is the best conductor because the Vaseline will melt and the drawing pin will drop. However, the question is not necessarily about this practical, it's just about conduction in copper in terms of the motions of particles. So to get your 6 mark, you want to get roughly 3 marks for talking about general conduction and then 3 marks for specifically saying it's a metal, so it's a slightly better version of conduction. So your first 3 marks, you want to talk about your ions in the metal or the particles. So these particles at the hot end gain energy. They vibrate with increasing amplitude, or you could say with more kinetic energy. They transfer their energy to other neighbouring particles by collisions, and this will continue throughout the body of the metal. For your next 3 marks, you want to talk about the free electrons because it's a metal. So copper has free electrons, which also gain energy at the hot end. They move towards the lower temperature end, the cold end, and they transfer energy more quickly. The next question is about convection, a different form of heat transfer, and it's talking about the practical we looked at in the lesson. Explain why the coloured water moves in the way shown above, and that's because hot water rises because it is less dense. You also could have said cold water sinks because it is more dense for both those marks. And part II, why is it not suitable to put a hot radiator at the top of a wall to warm up the room? And that's because hot air rises, therefore the air below will not be heated by convection. And here's the mark scheme for part B of that question. The final type of heat transfer is radiation, and this question is about a practical we can do to see whether a silver can or a black can absorbs infrared radiation better. So for this 6 marker, we have to talk about 3 variables that were controlled during this practical and why they were controlled. So I've put all the different answers down below. You only needed 3 of them with their explanation to get the full 6 marks here. Pause the video and write in 3 of these and their explanations, or mark the work you've already done. In lesson 4, we looked at insulation. So this is a 6-mark question explaining how different types of insulation can reduce heat loss by conduction, convection, and radiation. The 2 types of insulation are fiberglass and replacing single glazed windows with double glazing, both of which have a reflective coating on the glass. To get all 6 marks, you want to talk about all 3 types of heat transfer. So for conduction, there is a gas or a vacuum in the space between 2 panes in our double glazing, and that's a poor conductor, which reduces conduction through the window. And in our fiberglass, there are pockets of air trapped inside the fiberglass, and that reduces heat loss by conduction as well, because air is an insulator. For convection, this is mostly reduced by the fiberglass, and that reduces heat energy getting into the loft, and therefore there won't be as many convection currents formed in the loft space. And the last one is radiation. So there's a reflective coating on the glass, and this reduces heat energy loss by radiation, either by reflection or emission. And then the surfaces of the fiberglass insulation are shiny, and that reflects radiant heat back into the house and reduces the heat radiated into the loft. Next, we looked at payback time. So we've got this question where we've got a pie chart showing where a house loses heat energy, and we've got to do a bit of problem solving to work out which section of the pie chart refers to which part of the house. So if we read through it, the percentage energy loss through the walls is the greatest. So the largest section is 35%. That must be our walls. Then it says windows and drafts have equal percentage energy loss. So there are two that are equal at 15%. One is drafts already labelled, and the other one must be windows. And our last point is that the windows and the floor add up to the percentage loss through the roof. So if 10% was our floor, if we add that to our windows, 15%, we get 25%. So that must be our percentage lost through the roof. For part B, explain how fiberglass reduces energy loss in the loft by convection. For the first mark, you want to mention that fiberglass is an insulator, or it contains air or air pockets, or you could also state that because it's that insulator, it reduces conduction through the ceiling. The second mark is saying because of that reduced conduction, because there's less heat in the loft, this will then reduce convection currents forming in the loft. Part 2 of this question contains a graph, and then we've got multiple choice. We've got to pick 3 correct statements here. So let's go through them one by one. So every 5 years, the required thickness of loft insulation increases for our first statement. This one is not true because you can see from 2005, 2015, it stays constant, so that one's not true. The next one, we need to read some numbers of the graph. The required thickness of loft insulation 2000 is 8 times thicker than in 1970. So in 2000 is 200, and in 1970 it is 25. So 8 times 25 is 200, so the second one is true. The third one, in 1960, houses did not lose any energy through their roof. That's not really what the graph is showing. It's just saying how much loft insulation there was. So this one is not true. Number 4, a house built in 1980 needs 210 millimeters of loft insulation to bring it up to 2015 standards. So this is 1980, 60, and 2015 is 270. So the difference between those two numbers is 210, so that one is true. Number 5, the general trend of the graph indicates the required thickness has been increased at an increasing rate. That is true. A curve that goes like this means it's increasing at an increasing rate. And the final one, the required thickness of loft insulation will remain constant after 2015. We don't know that, so we can't answer that. So that one's not true. So we got 3 boxes ticked. Part III of this question says we're installing new loft insulation. It's got a loft area of 120 meters squared. That's in bold, so we're going to need it. And we've got 3 different types of insulations here. Calculate the payback time if insulation 3 was used in the 120 meter square extension. So the first thing I've done is copied our equation for payback time. This is not on page 2. You have to have this one memorized. It's the only one you need to memorize. So it's our installation cost divided by the savings per year. So we're looking at insulation 3, just this one here. We've got our installation cost per metre squared, the estimated savings per year, and then we are going to calculate the payback time. Firstly, we want to calculate our installation cost. So our installation cost is going to be £4.50 times by 120, which is equal to £540. That's what the first mark is for here. And then you're going to do £540 divided by the savings per year, 98, and you get 5.5 years. So you get the mark for either saying 5.5, 5.51, or you could round it up to 6 years, but I wouldn't bother here. The final part of this question is a little bit complicated, and I think it's a lot of work for 2 marks, and there's loads of different ways you can do it, but I've put it out in the most clear way that I can think of. The homeowner is considering installing insulation 1 as its cheapest, but the builder says that insulation 2 should be installed as it saves more money over 40 years. Explain with calculations who is correct. So for insulation 1, I worked out the installation cost. It's £3.50 times 120, £420 total. Over 40 years, I've taken the savings per year, times it by 40, £3,360. The difference between these amounts, so that's the savings, but we take away the fact that we had to pay for it in the first place, is 2,940. I did the same maths for insulation 2 and the difference was 3,774. So the savings for insulation 2 was better over 40 years. The builder is correct. And here's the mark scheme for this question. For that last part, there's loads of different ways that you could have picked up the marks, so have a look at some of the different methods. This revision question is on density and then convection. So the first part of the question says we have a volume of 80, 104 kilograms of air. Use an equation to calculate the density and state the units. So the equation we're going to be using is mass divided by volume. Our mass is 104 kilograms. I'm including the units for a reason. Our volume is 80 meters cubed. So we type that into our calculator, you get 1.3 for our density. Our units, we take the unit from the top of our division, kilograms, we put a slash because there is a line here, and then meters cubed underneath our line, so next to our slash, kilograms per meters cubed. Part B is now talking about a convection current. We have a radiator and we have 3 points in the room, A, B and C. Where is the air going to be the hottest? It's going to be A, because hot air rises because it's less dense, and that helps us with part 2 here. Where is it the least dense? Also A. And give a reason to your answer, and we're going to say hot air rises. And here's the mark scheme for that question. This revision question is on heat transfer, and it's discussing how a solar panel works. So the first part, explain in terms of particles how heat energy conducts through the walls of the copper piping in the heat exchanger. The key word there is conducts. We're going to talk about conduction for 3 marks. So you want to talk about your particles vibrating more or faster as they gain energy, colliding with their neighbours, and because it's copper, we can also mention there are free electrons that also pass on the kinetic energy, and that speeds up the process of conduction. For part B, explain why the liquid circulates in the direction shown. That's because convection currents are forming, because hot liquids are less dense and they rise. And then we have a maths question about this solar panel. So it's saying we have 960 joules of energy per second from the sun. Only a third of it is used to heat the liquid. But it says calculate the amount of energy given to the liquid per second if the panel has an area of 2 meters squared. So the first thing we'll do is we've got 960 joules. That's per square meter. So we're going to times it by 2. And that means we have 1,920 joules coming per second. And then we're going to times that by a third because only a third of it is used. And then we get 640 joules of energy given to the liquid per second. And here's the mark scheme for that question. This question is about our density practical. We've got description of the practical there and our results, which are going to help us answer questions on the next page. The first part says one member of the group claims the water has a density of 1 gram per centimetre cubed. Explain whether she is correct. So she is correct, and that's because if we have a look, every time our mass goes up by 10, our volume goes up with 10 as well. So if we have increases of 10 by mass and volume, 10 divided by 10 is 1. Every time we have 1 gram of water, it is 1 centimetres cubed as well. The mass and the volume are equivalent. Part B, having a look at our results at the bottom of the page. When did they start adding the steel ball bearings? So you can see between 40 and 50, instead of going up by 10, it jumps up by a larger number. So I'm going to put 50 down, but any number between 40 and 50 would be acceptable because we don't know exactly at what volume they were put in. And part II wants us to explain that. The mass values stop increasing by 10 after 40 centimetres. Part C, use an equation from page 2 to calculate the density of steel. So we're going to do mass divided by volume. And this looks a little bit hard at first glance, but we need to work out the mass of our ball bearings. So after 40, we can tell we started to add our ball bearings. So I'm going to look at the difference between, for example, 50 and 60. So I'm going to do 266, take away 187, and I'm going to get 79. So that's the difference in mass, and that's across a volume of 10 centimetres cubed. So I'm going to do 79 for our mass divided by 10 for our volume, and I'll get 7.9 grams per centimetres cubed. And for part D, 2 improvements that could be made to this experiment to get a more accurate value. So when you see more accurate, you want to be thinking about the resolution of your equipment. That's how many decimal places you can measure to. So for 2 marks, you could say better resolution measuring cylinder and better resolution balance. You wouldn't get any marks, so if you just said better resolution, you've got to be specific. What piece of equipment are you talking about each time? And here's the mark scheme for that revision question. This question is about heat transfer with conduction and convection in a metal saucepan. So you want to talk about conduction for your first 2 marks through the saucepan base. Particles near the bottom vibrate more and they pass their energy along. And you also want to mention the free electrons which transfer energy. And then the water, we have convection. The particles in the water as they heat up move further apart. They're less dense and that water rises and that sets up a convection current. And here's the mark scheme for that question. The last revision question is about convection, and it shows us the practical. Part A, we're just stating that it is convection because it involves liquid rather than a solid, which would be conduction. And part B, we're describing what happens. So the particles gain kinetic energy, they vibrate more or move faster, and therefore they move further apart. And part II, this forms a convection current because hot water is less dense and less dense water rises. Here is the mark scheme for that question.